Look at some illustrations here where we could have action-reaction forces. And remember, these action-reaction forces are equal but opposite. I can remember one time my aunt took me to go see Santa. Santa came in a helicopter, really like, I don't know, I don't want to say shattered my image of Santa because I was hoping to see him fly in on a sleigh. My aunt told me he was going to fly into the parking lot at the local mall. And he came in on a helicopter, and I was like, oh, Santa. I was excited. I saw the helicopter. It was a red helicopter. I was very excited to see Santa coming in. The thing that I think that the organizer didn't realize was Newton's third law. Because what happens if you're in a parking lot when there's already been sand and salt poured down on the parking lot and it's become like this grit layer on the parking lot, is the helicopter, sure, hey, you know that as this blade spins, the helicopter is held up. But it spins like a fan. And so there must be a force of the air acting up on the helicopter. That's what keeps the helicopter up. But if there's a force of air on helicopter, what's the action-reaction force?
Excuse this interruption. We have students with the last name
Yeah.
through T.
Force of helicopter
Had your photo taken. If you could please make your way down to
on air.
Once
And
again,
if you want to impress kids,
through T. Thank you.
fly Santa Claus in. But if you want to make a whole group of like 100 kids in a mall parking lot cry, bring them in on a helicopter and throw salt and sand in their eyes. And that was like, it's like a, I want to say like an anchor moment in my life. Yeah, absolutely. So like, be careful, but it's Newton's third law. It's not like it was ever going to not be there. And remember, that dot means acting on. Dot means acting on, not relative to. That's velocity. Okay, so a slight difference in our notation from relative motion. I want to think about squids. Squids, because you know if you ever have calamari, there's actually an empty cavity inside of a squid. And sometimes people think of that cavity as being like their head. It's like a bladder. Not for urine, but it's a fluid-filling bladder. And if you ever have calamari and you eat calamari rings, like deep-fried calamari ring, what they're actually doing is they're taking that bladder and they're slicing it into rings because it was already hollow. So it's just going to make you like these nice, rings that you can batter and deep fry, right? I personally really like calamari rings. It's nice. Easy to make, too. Anyway, I want to say that this is inside of the squid. And inside of a squid, we've got water. What the squid does is it draws in water and fills up that bladder with water. Another thing about squids is that squids have been on Earth for a very long time. Longer than sharks. And they were top-end predators well before sharks were. They predate dinosaurs by ages. They're not vertebrates. They're before skeletons were a thing. And they were the top-end feeders. One of the things that made them a top-end feeder is that they have a sharp beak that allows them to basically bite into anything, kind of like a very strong parrot. They have tentacles that let them wrap themselves around animals and crush them to death or just hold on to them while they devour them. That's amazing. But the other thing is how fast they can jet. And the way that they achieve this isn't just by flapping their tentacles. It's by squeezing the water out of their insides and shooting it out like a jet stream out their back end. Around where their mouth is, but a different hole, okay? And so what they actually do is, if there's inside water and there's outside water, they actually squeeze this cavity, this bladder, and there's a force of the inside water pushing on the outside water. And that pushes the outside water this way. Think of the water itself, kind of like the air underneath the helicopter being something that can be pushed. But if there's a force of the inside water pushing on the outside water, what's the action-reaction force pair? Outside on inside. And when you eat meat, you're eating muscle. And when you eat calamari, you're specifically eating squid muscle. And that calamari ring is a really strong muscle that's designed to squeeze water out. That's what it's for. And it's such a great little treat when you go to the restaurant, a little appetizer, because this thing was designed well before the sharks, which was well before the dinosaurs, to go and eat as much as they could. And they were top-end predators for ages, longer than humanity will probably exist as a species. And that's kind of cool, I think. Now the thing is, humanity comes along and they say, squids are awesome. I love squids. Why don't we make, yeah, let's eat them. But also let's make some technology. This is called biomimicry. And what humanity says is, hey, why don't we suck in air into the front end of what we're going to call a jet engine. We're going to force the air into a little area, and then we're going to force it out of a small aperture on the back end. This is a jet engine. We're not going to have it expanding and contracting like our biological cousins, the squid. We're going to mechanically draw it in with a turbine or with a cyclonic intake, and we're going to force it out through a small space. And what we're basically going to have is inside air pushing as a compressed stream on the outside air. And that outside air is going to get pushed back, and as a result, we're going to have the inside air, force of outside backing on inside, pushing our jet forward. We're just stealing the idea from squids. Hey, they were successful for a while at getting around quickly. Why don't we do it too for a while, right? And we probably go extinct well before they do. But that's okay. In the meantime, I get to go to, I don't know, California, Cuba, or, I don't know, Iceland in a short amount of time because of this technology. This is important stuff, right? Let's think about swimmers. Swimmers do not use a jet principle. They don't use a helicopter principle. My goodness, if this swimmer was using a jet principle, I don't want to even imagine where she'd be squeezing. Never mind. She's swimming. So when she swims, you know that there's going to be an arm that comes down here, right? We've got an arm that comes down into this position. And when her arm descends down into this position, what's she going to do to the water with her hand? Push back on the water. So we'd have a force of, I'll say S for swimmer, on water. The action-reaction force pair says that there would be a force of water on swimmer. Now it happens to be the hand of the swimmer, and the swimmer's going to do a bunch of other things, like maybe getting a little bit of push from her feet there as well. But a lot of the thrust, a lot of the force is going to come from hands. We know that about swimmers, right? And, you know, this is something that humans were doing for ages. And then a few years later, people decided that they didn't want to get wet so much, and they wanted to carry cargo around. And so we came up with stuff like this, a very Canadian sort of thing. Put our cargo in the front. You know, one time I was in the Amazon rainforest, and I watched a whole group of kids in a canoe, and they were all wearing school uniforms. And what I didn't realize, it was an indigenous community I was visiting, along with my wife. We were going, because she's from South America, so we went to go visit this community. And I saw all these kids in this little canoe, and it turns out that canoe was the school bus. And there was a guy paddling, and I didn't know I was seeing the school bus at the time, and I found out later like what I was seeing. And they were going up and down the river because there was no road system. It was all rivers, right? And for ages, even now there are places where things are only accessible by river, but for ages in Canada, river was the main avenue of transport, right? I mean, post-colonization, we got roads and everything, but this is an important technology. So when I travel in a boat, we know, just like the swimmer, force of, I don't know, paddle on water, but then we're also going to have a force of water on paddle, driving the boat forward. Action-reaction force pair, right? So that paddle is really connected to the boat. And if you're a canoeist, then you know all about how this works. You know your J-stroke and all that sort of thing. I love to go canoeing myself, but it's still action-reaction. Now, slightly less folksy and fun and historical, whatever. Well, maybe it's historical. Cannons. If we want to make this fun, because we don't want to be violent, you can make this be like a clown's cannon. We'll put polka dots on this thing. We'll make it be like a circus ball. I don't care. However, when this ball gets fired, think about the ball. It gets shot this way. I know that there's a little explosion that's going to happen back in here, but essentially it's the cannon that's launching this thing. If you want to make it less violent than an explosion, this one looks like it's on fire, make it be a spring-powered cannon, whatever. We could say that there's a force of the cannon acting on the ball, and that's going to propel the ball forward. What's the action-reaction force that's going to go with this one? Ball on cannon, right? That means that there's going to be force of ball acting back on the cannon. Now, I set this up in kind of a contrived way, but I actually set it up in a way that I've seen at local forts. I've gone around to look at the historical forts. There's one in Kingston, there's one in Niagara Falls. I've seen some in the Caribbean. Like pretty much every colonial era place still has like some stone forts still kicking around from back in the day. And oftentimes they'll have the old cannons sitting there. And oftentimes you see this. If you go to Quebec, you'll see this. Cannons sitting with a ramp behind them and like a little stop block in front of them. Why is the ramp there? Anybody know? Yeah.
When the cannon shoots, it's going to move back.
Yeah. And there's even an R word for this. It's called recoil force. And that recoil force is going to drive the cannon up the ramp. And then the ramp is there just because we know things roll back down ramps, back into position, right? And so people would have some variation of this for their cannons. I mean, even today, the Navy has some variation of this. And I was fortunate enough, my wife was friends with a fellow who's an engineer for the Navy out of Halifax. And he got to give us a tour, you know, like just him and my family tour around the Halifax shipyards. And we got to see the modern version of this. Now, the modern version of this doesn't use ramps because the cannons are bigger now. They use enormous electromagnetic shock systems. But they still have to deal with the recoil. Otherwise, the cannons would tear themselves off the deck of the ship because the cannons are that much more powerful now, right? I mean, they also have rocketry and things, not just projectiles anymore because the things they're shooting have a sustained power force. But they still shoot them off initially like it's a bullet. And then the power system kicks in and goes off like a rocket. And so there has to be a system in place to deal with the recoil. If you're somebody, you know, like myself, my family is a hunting family. My dad's not a hunter, but my uncles decided I needed to learn how to shoot a rifle when I was a kid, just in case I wanted to go deer hunting, which I have no desire to do, by the way, okay? But I can remember having to, and here is me, little 10-year-old me, with my rifle, just at a rifle range, didn't ever shoot an animal or anything like that, but I got my rifle. You know that bullet, when it goes, has got a force that's going to push it forward, right? Force of gun on bullet, if you like. But isn't there going to be a reaction force on the rifle? Force of bullet on gun? The thing is this. Doesn't a bullet have a small mass? Think about Newton's second law. F equals ma. And think about scaling. If the bullet has a really tiny mass, and the force of gun on bullet is a big force, isn't that going to make the acceleration a really big value? However, if I take this gun and I put it up against my body, and my uncle would say, make the rifle and yourself one. What he really meant was make it so there's no gap between you and the rifle and really hug it tight. And so what that would mean is that the combined mass, me and the rifle, would be a really big mass. But isn't the force of gun on bullet and force of bullet on gun the same F value? Notice those two F's are the same size? If the F value is the same size, but the mass of me and the gun is bigger than the mass of just the bullet, what's going to happen to the recoil acceleration? Much smaller, right? And so the whole point is you wouldn't want to have a big recoil acceleration because it would push you backwards, right? Now, if you don't have the gun right up against your shoulder, the gun will accelerate backwards. It's called kickback, and it can dislocate a little kid's shoulder. Now, I don't actually think you should take little kids to the rifle range. I'm telling you about my lived experience, okay? I think that's a silly thing to do. But I do know that there are people around these parts that go to the what you call it, with the paint gun. They go with paint guns. They shoot each other with paint guns, not like rifles or whatever. But these air rifles, they also have kickback. And it turns out that if you have a powerful air rifle at the air rifle range or playing paint gun, you'll also want to have it butted up against your shoulder because kickback actually can cause like a little bit of bruising to your shoulder. And I know I went paint gunning with my son. It was a birthday party, and he had a powerful paint gun. And he had it like not right up against his shoulder. And he did. He got like a serious little bruise on his shoulder. You know, he didn't know what was going to happen. And then he knew. But it's because of this, right? We want to make sure that the mass of the paint gun and our bodies are kind of combined together, snugged up against each other, so that we minimize the kickback. I think that just makes sense. It also explains why when cannons are fired off of ships, the whole ship doesn't accelerate backwards. Because the ship is massive. If we mount this cannon onto like an old-timey, wooden boat, the whole ship doesn't accelerate backwards because its mass is enormous compared to the little bitty mass of a cannonball, right? I'll sort of pause there. Oh, before I do though, did you know that every time you push on a wall, the wall pushes back on you? Just like when you push on somebody's hand, the hand pushes back on you. Push your hands together like this and try and press on each other. You know that one hand pushes back on the other. But if you take your right hand and you press it against the wall, what people don't often think about is the fact that the wall is also pressing back on you, right? That's something to sort of keep in mind, right? That Newton's third law is all around us. It is weird, but true.